Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthew Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples.
Hello, and welcome back to Stories from Space. I'm your host, Matt Williams, and today I'd like to go back to Mars. Specifically, how all of our current astrobiological studies and efforts are focused there, and how these will be revolutionized in the coming years thanks to the Mars Sample Return mission and quite possibly the Tianwen-3 mission. As China recently revealed, they plan to send their third robotic mission to Mars, which includes a sample return, and that is expected to launch by 2028 and return by 2031, which would beat NASA and the ESA's mission by 2 years. And much of that has to do with recent budget cuts for NASA, which we'll look at in a bit. First, there's the significance that a Mars sample return mission will have, and the long history of planning that has gone into them. Now, to break it down, a Mars sample return mission is something that space agencies have been contemplating for a long time. And the reason is because, given the distance to Mars, sending the necessary equipment to conduct a detailed analysis of its soil is still very, very difficult in spite of all the advances we've made. And as the Apollo missions and the Soviet Lunokhod missions demonstrated, returning samples from a celestial body, that allows you to learn more about its composition, evolution, its history, more than any kind of sample analysis you could conduct in situ or on the scene. Fact of the matter is, the equipment is just too heavy and too cumbersome to send as part of a mission, whether it's a robotic mission or a crewed mission, it doesn't matter. And even the Curiosity and Perseverance rovers, which are the most advanced mobile laboratories ever created, even with their UV and X-ray spectrometers, which have provided some extremely detailed analysis of Mars soil samples, the kind of analysis that will provide scientific returns for years and even decades to come, that can only come from a sample obtained directly from the planet or moon, brought back to Earth and analyzed repeatedly with all kinds of laboratory instruments that take up a better part of a room. And once again, the lunar samples really illustrated this. Thanks to the moon rock samples that the Apollo astronauts brought back, scientists are still making profound discoveries about the moon. In the first place, this included the mineral composition of the moon, which led to the giant impact hypothesis, which essentially states that the Earth-Moon system, as we know it today, it was created by an impact that happened roughly 4.5 billion years ago, shortly after the Earth formed. And this was a time of incredibly turbulent activity in our solar system. Large objects were being kicked and perturbed out of their orbits and thrown into the inner solar system. And the current theory is that a Mars-sized object named Theia, its orbit was disturbed by the movement of the gas giants, and it was hurled towards the inner solar system and it collided with Earth, and this created a massive cloud of magma and liquefied rock, and these slowly condensed into two separate bodies, the Earth and the Moon. And the Moon was originally much closer to the Earth, but it then began to migrate outwards into its current orbit, and the two have co-evolved ever since. And this was derived from the fact that when they analyzed the Apollo rock samples, scientists found that they were very, very similar in terms of composition to Earth. And combined with other experiments that the Apollo astronauts left behind, like seismometers that measured moonquakes, they were able to determine that the moon's structure was likely, much like Earth's, differentiated between a silicate crust and mantle and a metallic core. And from magnetic readings of these samples, they determined that the moon had a magnetic field in the past, much like Earth does today, much like Mars did many billions of years ago. And they even found traces of water, which at the time were attributed to contamination, but reanalysis later on revealed that no, that water is indigenous to the moon, and that it forms all across its surface as a result of solar wind interacting with elemental oxygen, giving us H2O. And it was attempts to characterize the moon's water, looking for hydrogen in the surface material using spectrometers, that we stumbled onto the very large deposits of water ice in the South Pole Aitken Basin, in the permanently shadowed craters there. So suffice it to say, sample return missions can reveal a wealth of information about a celestial body, and they can lead to other discoveries. They can point us in the direction of other phenomena and other mysteries. So NASA and other space agencies have been contemplating a sample return mission since the days of the Apollo era. In fact, the Mars sample return mission was part of a wider effort to contemplate mission proposals that went beyond Apollo, which of course were focused on Mars. Crewed missions, the necessary launch vehicles to get astronauts there and back, and yes, obtaining Martian soil and rock samples similar to the moon rocks brought back by the Apollo astronauts. The Soviet Union planned on mounting similar missions. These included the concept for a Mars flyby and also a robotic mission that would return samples from either Phobos or from the Martian surface. Now, after the Apollo missions were complete, these plans were largely shelved and collected dust for many decades as both the Soviet Union and NASA began to focus on objectives that were closer to home and more budget-friendly, and that, of course, included the development of reusable spacecraft, such as the Space Shuttle and the Buran, and also the development of technologies that would allow for long-term stays in space. In other words, space stations. However, beginning in the 1990s, there had been renewed proposals and renewed interests in Mars exploration, and consistent with that, ideas for sending a sample return mission have also been picked up and dusted off and updated to a significant extent. And beginning in the 21st century, NASA began putting out the call for mission concepts and received several proposals from industry contractors. And so the nature of the Mars sample return mission, at least as NASA envisions it, it's changed considerably and evolved considerably over the past 20 years. And what came of these plans ultimately was that the Perseverance rover, it would carry a sample cache, unlike Curiosity. Curiosity is capable of drilling core samples and then testing them in its internal laboratory, and certainly Perseverance can do the same. But they also decided that Perseverance should be able to collect samples for future analysis and leave them behind for future retrieval. And originally NASA had hoped that that cache would be picked up by astronauts when they arrived on Mars in 2033. However, with delays and budget shortfalls and the number of developments happening in between that have sort of raised doubts about whether or not NASA will actually be able to send crewed missions to Mars starting in 2033, other options began to be explored. And what resulted from this was the current joint plan between NASA and the European Space Agency for the Mars Sample Return Mission, known by its abbreviation MSR. So much like the old plan, this one still counts on the Perseverance rover, it collecting numerous samples and leaving them in its sample cache and also in these little sealed containers on the surface. And that this time around, though, a robotic mission will be sent to retrieve them, and it will be launching before any crewed missions are sent to Mars. The timeline NASA is exploring right now is launching this mission made up of multiple robotic elements by 2028, and they would return the samples by 2033. Now, the various robotic elements of this mission include a sample retrieval lander which is built jointly by NASA and the ESA and carries all the necessary equipment to gather up the samples and send them up to orbit. And this will be done by Perseverance itself, which will drive its sample cache over to the lander and help load it aboard. And the ESA has included a robotic arm to help with that process. And NASA has also contributed 2 sample recovery helicopters to the mission, which are similar in design to Ingenuity, the small helicopter that Perseverance brought with it to Mars and tested all the requisite flight technologies involved. And so once the samples are all loaded aboard, the NASA-provided Mars Ascent Vehicle and its Capture, Containment, and Return System, they will launch for orbit, where a ESA-provided Earth Return Orbiter will be waiting to pick them up. And NASA and the ESA have also jointly developed the Earth Entry System, which is basically a heat shield for the Earth Return Orbiter to bring back with it. It will hold the samples and be fired into our atmosphere and retrieved once they safely touch down on Earth. So, as I noted, this mission would be prepared to go by 2028 and would be returning samples to Earth no sooner than 2033. Unfortunately, this past November, NASA announced that the project was on pause because a budget review looked it over and determined that it was just not feasible in the current budget environment. So NASA is being forced to review the sample return mission architecture and find ways to scale it back to make it affordable. And in the meantime, China has announced that their Tianwen-3 mission, which is the 3rd mission in its Tianwen program, all of which are robotic explorers being sent to Mars, it will carry a sample return package, similar to what they've been doing on the moon with their Chang'e program. And as they recently announced, this mission will also be taking off in 2028. But they plan to bring the samples back to Earth by July 2031, a full 2 years ahead of NASA. And if they, in fact, are able to do this, they will have beaten NASA to the punch. They will conduct the first sample return mission from Mars, and the scientific returns are likely to be very, very big. And this is one of several steps that China has taken in recent years, basically to demonstrate its growing power in space, its growing influence, and it's all part and parcel of their goal of becoming a superpower in space by the next decade. They intend to rival NASA at that point, and many of their proposed and declared objectives are very much in keeping with that. And that includes their proposal for sending astronauts, or taikonauts, to Mars by 2033 on the exact same timeline as NASA, which is, of course, going to overlap with their plans for building a moon base that would rival the Artemis Space Camp and the Artemis program, which they hope to have complete by 2035. So it remains to be seen if any of this can be done in the time allotted and the budget allotted. But it is clear, certainly to NASA, that they've got some competition, that China intends to rival them in every single mission capacity, and that a Mars sample return is one such capacity. It's got a very high importance. In any case, what will these samples tell us? What scientific returns are they likely to provide? And that is something that scientists have been asking themselves ever since the Viking missions landed on Mars. This was the first astrobiology mission, consisting of 2 orbiters and 2 landers, that went to the Red Planet for the express purpose of determining just how hostile its environment was and whether or not life could survive on the surface. Previous missions had provided ample evidence that the atmosphere was far too thin and irradiated and really, really cold, so it cast doubts on whether or not life could exist on the surface in any way, shape, or form. But the Viking landers were meant to obtain samples and analyze them in order to look for signs of potential biosignatures. So organic molecules and chemical elements that we associate with life, or which we know life depends upon or produces as a byproduct. And the results were inconclusive. Scientists could not say with any confidence whether or not the Viking lander had found evidence of organic processes or not. And these results were reopened in 2012 by an international team of scientists. They looked over the data and they concluded that, in fact, the Viking mission may have actually found evidence of extant microbial life on Mars. Unfortunately, that was not exactly a conclusive finding, so scientists are still waiting. There was also a reassessment done for data gathered by the Viking landers' gas chromatograph mass spectrometer, which indicated that the atmospheric sampling that the Viking landers performed, that the results they obtained were consistent with the presence of organic molecules, molecules like methane. And this is something that has since been confirmed by the Curiosity rover. Methane is known to exist on Mars and often creeps up from the subsurface, which could indicate decayed biological life or ongoing biological processes, but those are mere possibilities at this point. And this is why a sample return is going to be so invaluable. Scientists will be able to analyze them with very precise, very sophisticated equipment, and they'll be able to do it again and again. Much like the Apollo moon rocks have been examined multiple times over the years, sample analysis can yield information for decades to come, especially when you consider the fact that our equipment is only going to grow more sophisticated with time. So the results that we get from any samples returned from Mars, they're going to be subject to analysis and reanalysis over and over again. So if there is, in fact, biomarkers in the samples, sooner or later we'll find them. And this will constitute the first hard evidence that Mars does, in fact, support microbial life, likely in subsurface caches, and that indications of this can be found by digging into the bedrock, digging into the soil, digging into alluvial plains and clay minerals where liquid water once flowed and where life would theoretically have thrived. This would confirm long-held theories that while complex life, mitochondrial multicellular life may not have ever emerged on Mars, that simple microbes did. And if in fact we can examine that type of life, we can determine whether or not life on Earth and Mars co-evolved. So did Martian microbes have any kind of input on the emergence of microbial life on Earth or vice versa? Because we know for a fact that meteorites from both of our planets, they were created after impacts hit our surface and threw chunks off into space. And for Mars, it was a much easier process because of its lower gravity for it to send material our way. And if that material did in fact contain basic life forms, then it is possible life on Earth began on Mars. And that too is a long-standing theory. Bottom line being that a sample return mission would allow us to finally confirm that. But, of course, there's the possibility that the samples will yield nothing. No evidence of life, extant or otherwise, in which case scientists are simply going to have to wait upon crewed missions to Mars, which establish habitats on the surface, bring all the necessary research equipment with them, and study the surface and subsurface environment for weeks, months, possibly even years. And regardless of what it finds, a sample return mission at this point in our history, it represents the next major step in terms of our astrobiological efforts, our research into life beyond Earth and our attempts to find it in other planetary bodies and moons. Right now, just about all of our astrobiological efforts, the vast majority of them are focused on Mars. It's considered the most likely place to find life beyond Earth. There is speculation as to whether or not life could exist in Venus's clouds. There are plans to send robotic missions out to explore Europa and Ganymede and the other ocean worlds. And those are really going to start to come together in the next decade and well into the 2040s and 2050s. But right now, our eyes are still really focused on Mars. And so when the next major sample return efforts happen, they will be aimed squarely at the red planet. They will involve robotic missions at first, but these will be followed by crewed missions who bring back Mars rocks, much like the Apollo astronauts brought back moon rocks. I, for one, am very excited to see what we can learn from them. because we're not just talking about whether or not life once existed on Mars. We're talking about whether or not it still could exist today, and whether or not life on our planet and life on the red planet are related. Because that, too, is going to have extremely significant implications for our sense of self, our place in the universe, and also for how we go about settling on Mars if and when we decide to do that. If we're going to terraform, if we're going to build up a large society there, then we need to think about how this could impact indigenous life forms. Planetary protections are going to have to be applied. Exciting stuff. And like many other missions, many other breakthrough technologies that are going to be becoming operational, we're not going to have to wait long to see them. So it would be a shame if any sample return missions at this juncture are canceled or delayed due to budgetary problems. But as long as one space agency is willing to mount the mission and is willing to shoulder the cost, we will have Martian samples back here on Earth sometime in the next decade. Well, thank you for joining me for this latest episode. Tune in next time, where we will be talking about how human beings can settle on Saturn's largest moons, or the Cronian moons. We'll also discuss the recent attempts to resolve what is known as the Hubble tension, or the crisis in cosmology. And I will have some more exciting guests on to talk to us about the upcoming Europa Clipper mission, as well as Breakthrough Starshot and similar proposals for mounting missions to other stars. In the meantime, thank you for listening. I'm Matt Williams, and this has been Stories from Space.
We hope you enjoyed this episode of Stories from Space podcast with Matthew Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.